Okay, this is a gravitational potential energy problem where we have a block M. We have this like loop-de-loop track, and the block initially is at a height h. It moves down, it gains speed, it goes around the loop-de-loop, and then it goes out the other side. So the first part of this question asks us, maybe let's write this over here. What's the kinetic energy of the block when it reaches the top of the loop? So again, this is an energy conservation problem. So let's pick an initial position here when the block is at a height h at rest. And then we'll say maybe when the block is over here, it's going to be our final position. And we're going to say our initial energy, initial potential energy plus initial kinetic energy has to be equal to our final potential energy plus our final kinetic energy. And in this case, we're told that the block is released from rest, and so, well, it says the block starts from point P, so let's assume that it's released from rest. And so the initial kinetic energy is 0. And what we want to find is the final kinetic energy. So K final is going to be U initial minus U final. And our gravitational potential energy here is mgy. So let's call the ground y equals 0. And so our K final is going to be mgh minus mg2r. Right, so here, when the block is in the final position, its height is 2r above the ground. Or we can just rewrite this, if we want, as mgh minus 2r. Okay, so next, part B asks us, what's the acceleration of the block when it's at the top of the loop? The top of the loop, assuming that it stays on the track. And so we want to recognize here that when the block is going around this loop-to-loop, it's in circular motion. And so the acceleration is going to be v squared over r. And we're not given v, so maybe let's try to write this in terms of the other variables. So we just said that k final, which is 1/2 m v squared, has to be equal to mgh minus 2r. So we can use this expression to find an expression for v squared and plug that in for the acceleration. So here v squared equals 2gh minus 2r. Right, so I just multiplied both sides by 2, divided both sides by m. And so my acceleration then must be 2gh minus 2r over r. And then the final part of the question, C, says what is the least value for h for which the block will reach the top of the loop without leaving the track? Oops, let's put a T in there, without leaving the track. So the idea is if you start the block too low, it won't have enough energy. It'll go down, it'll go around, and then it'll sort of like fall off the track. Right? So that's what happens if you release it from too low. If you release it from high enough, it'll actually stay on the track the whole time. So, okay, so let's think about what happens at the top of the track. Actually, I'm going to write this over here. So at the top of the track, let's draw a free body diagram for this mass. It has a gravitational force acting on it, and it has a normal force from the track pushing it down. And the acceleration, as we said, is v squared over r, or this 2g h minus 2r over r. That's the centripetal acceleration that keeps it moving in a circle. And so if we set up F equals ma, where F is the net force, then we say mg plus the normal force has to give us ma, or m 2g h minus 2r over r. And the point at which the block loses contact with the track is when the normal force reaches 0. And so that's the point at which we know we have sort of the minimum speed. And so what we need to do is solve for h in that situation. So it turns out, let's see, I really feel like I need more space here. So let's solve this. We have, continue this here, mg equals m2g h minus 2r over r. There's an m on both sides, and there's a g on both sides, so we can cancel those out. Let's multiply both sides by r. So put an r over here. And then we have r equals 2h minus 2r, or r over 2 equals h minus 2r, or h equals 2r plus r over 2, which is the same as 5/2 r. So h has to be a bit more than 2r in order for the block to stay on the track.